Now that you know the rules for basic nature of a compound, let us see some examples of it. First, in the first one you take methylamine, then you have 2 methyl groups, and then you have 3 methyl groups. That is, you have taken primary, secondary, tertiary, and ammonia and aniline. Now you have to arrange these in the order of their basic nature. First, if you take gas phase, then you have 3 greater than, 2 greater than, 1 greater than, 4 greater than 5. Whereas if you take aqueous phase, you have tertiary greater than, primary greater than, that is secondary greater than, primary greater than, tertiary, and then you have ammonia which is greater than pH NH2. Now, why this is different for different solvents and where come the difference between them? Now, if you take aqueous solvent, here the basic nature is dependent on 2 factors, that is electron donating capacity of nitrogen and solubility. And if you take gas phase, there is no question of solubility, so the only outcome is electron donating capacity. So we can conclude that for this solubility you have tertiary greater than, tertiary less than, secondary less than primary, and for electron donation capacity you have tertiary greater than, secondary greater than primary. Now on clubbing these 2 factors, remember you have methyl here. Only for methyl you have 2 greater than, 1 greater than 3. Now this is obvious. 5th one is least because nitrogen lone pair here is involved in resonance with this pH ring. As a result of it, this lone pair is less available for donating. So this is less basic than all. Now what if you replace this methyl with ethyl? Now in the gas phase the result is same, that is tertiary would be greater than secondary than primary, and you have 4 greater than 5. This is because you are already taught in tertiary the nitrogen has more electron density. This is because all these 3 methyl groups, as in the previous example, or these ethyl groups, donate electrons by plus I effect. Now if you take aqueous phase, you have tertiary greater than, that is secondary greater than, tertiary greater than primary. So as you can observe here, there is a difference between this ethyl and this methyl. Now one more important thing which you are supposed to know is guanidine. The guanidine is the most stable organic base. The structure of a guanidine is shown here. Now as if you see, this nitrogen is more basic. You may think that this nitrogen is sp2 because it has double bond. So how can it be more basic as sp2 has more electronegative? The reason is that it's not only dependent on the sp2 or sp3 character of it, but here you have a resonance structure where this nitrogen donates its electron to this carbon, and this bond shifts here. You are going to get negative charge on this nitrogen. As you can see, the negative charge on nitrogen is increased, so this is more basic because it is more available to donate its electrons. Now you got a compound like this one. If you see, 3 resonating structures are possible for it as shown here. First one is this one. Now if you transfer the lone pairs of this nitrogen in this direction and this here, you are going to get a structure like this one. And if you do the same thing, that is if you transfer the electrons in this direction and this bond in this direction, you are going to get this compound. Now if you carefully observe, these three resonating structures are identical. As written here, these three resonating structures are identical. Now you are taught in your GOC that if the resonating structures are identical, then the compound is more stable. So as a result of it, the form conjugate acid is more stable. So this guanidine is most basic. Now let us see the next part of it. Here are a few more examples regarding the basic nature of amines. Now you are given in the first example 3 compounds, and you are asked to arrange them in the order of the basic nature. Now if you observe, the order is 1 greater than, 3 greater than 2. This is 3 and this is 2. Now the result is simple, because here the difference between them is you have carbon atom here, oxygen atom here, and chlorine atom here. Now if you observe, the electronegativity of oxygen is greater than, chlorine is greater than carbon. As a result of it, this pulls electrons, giving a partial positive charge on this nitrogen. So you have this as less basic, so you got 2 on the last. And if you see, next comes chlorine, so it is third one, and next is first one, where you have carbon which donates electrons. Now in the next example, you have nitrogen in the cycle, and you are asked to arrange them in the order of the basic nature. Now the order is 4 greater than, 3 greater than, 2 greater than 1. This is because as you keep on increasing the size, the number of carbon atoms increases. So here you have 2, here you have 3, here you have 4, here you have 5. So as a result of it, you have more plus I effect. That is, the plus I effect is increasing. So this is more basic than all, and next comes this one, and next comes this, and then finally this one. All these things you have learned in your GOC. Now these are just recapitulation of them. And next you are given this amide CONH2, and you are next given replacing this C with a pH ring. Now for this case, this second one is more basic than first one. You might be knowing the reason, but let me discuss it again. The thing is that in the first case, you can see nitrogen donates electrons to this electrophilic carbon, owing a negative charge on this oxygen and a positive charge on this nitrogen. So the resonating structure is this one. Whereas if you see this structure, there are 2 possible resonating structures. One is, there is 2 possible cases, not 2 resonating structures. One is this pH ring donating electrons to this C double bond O, and next one is this nitrogen donating electrons to this C double bond O, as shown here. Now as you can see, this C double bond O pulls electrons from this nitrogen less than this C double bond O pulls electrons from this nitrogen. This is because this pH ring is donating its electrons to this C double bond O, and the positive charge here is somewhat satisfied by this negative charge. So this nitrogen has comparatively more lone pair, so this donates it effectively. So this is greater. Now let's go to the next part. Let us come to the last part of the basic nature, where you have to tell the basic nature of substituted aromatic compounds. Now consider these 4 compounds, where first you have aniline, and next you have any substituent, say S at ortho position, and next one at meta position, and next at para position. Now depending on this variation in S, you are going to find out the basic nature order for this, and what you are going to expect, and what is determined experimentally, and the reason for it. First consider a substituent which is plus I and plus R or plus H even. The example for this one is CH3 group. Now if you see the net effect here is plus effect, which is donating effect. Now in general, what do you expect? We expect that ortho greater than, para greater than, meta greater than X. This is because for CH3, since it is plus I, it donates electron more. So first you have ortho, and you know that plus H character is more at, or is occurring at ortho and para positions. So you observe this one, but experimentally it is observed that ortho is at the last. The reason for this is ortho effect. Now in a short while we will see what this ortho effect is, and you might have learnt it in your GOC. It's just a recapitulation of it. The next one includes minus I and minus R effect. The example for this one is NO2. The net effect is negative here as shown. Now if you observe, you expect that X greater than, M greater than, P greater than O. Now that is what observed experimentally is, so there is no reason for it, and you know the reason from your GOC. And the next one is minus I and plus R group, say for example OCH3 group. The net effect is positive because plus R effect is greater than minus I effect. Now for this one you have para greater than, ortho greater than, X greater than M. This is what we expect, but experimentally it is observed that para greater than, X greater than, ortho greater than M. Now if you observe these two carefully, you can see that this ortho is tending to be less basic in this one. The reason for this is ortho effect, as I have told you. Now let us see what this ortho effect is. Consider an aniline, where as shown here. Now if it is unsubstituted, then the lone pair here is oriented such that it is perpendicular to the benzene plane. As only then the resonance is possible between this lone pair and this benzene ring. And now next one is, if you have any substitution at ortho position, say S here. Now because of presence of this S, this will repel the lone pairs of this nitrogen. As a result of it, this S turns the lone pair of nitrogen out of the plane. As a result of it, effective resonance is not possible. So because of presence of this S at ortho position, this nitrogen is less donating its electrons, or you can say that this nitrogen is turning out of the plane, so its basic nature is comparatively decreased as for the case of this one or this one. Now this is what you are taught in your GOC chapter, ortho effect for COOH group, where you have substitution at this here. Now the same is the case with this NH2 group. Just recapitulate your GOC and go through that GOC, you will be more comfortable with this. Now that we are done with the physical properties and the methods of preparation of amines, let us come to the chemical properties of the amines. Now here I have with me a table which shows the different tests for different amines. Now the chemical properties, the study of these things is very interesting because this involves the separation of these primary, secondary and tertiary amines, and there are many logics between them, and the reagents which we use, the reaction that is occurred is very interesting to learn. Now for your better sake, I have given you this table so that you can quickly go through it during the time of your exams. Where you have any competitive exams, you can quickly go through it and see what it is. Now first one is Cobalamin test. For the Cobalamin test, primary only reacts whereas secondary and tertiary doesn't react. Now the second one which we'll be talking about is Hinsberg reagent. Now, you'll come to know all these reagents in the theory or in the problems. Now for the Hinsberg reagent, you have primary which is reacted completely, and secondary reacts only half of the test, and tertiary won't react at all. Now for HNO2, both primary, secondary and tertiary react, but the way in which they react differs. So as a result of it, you'll be able to separate the primary with secondary and tertiary, or the other way around. That is way differs here. Now the reaction of this with HNO2 with secondary is very famous one, and that is called as Lieberman's nitroso test. You'll come to know what it is in your problems. And next important test is Hoffman's mustard oil test. And for this test, primary reacts completely to the test, whereas secondary responds only to the half of the test, but the tertiary doesn't respond at all. This is similar to this Hinsberg reagent, as you can observe. And the next one includes oxidation, which is with KMnO4. For this KMnO4, all these reacts except tertiary, that is primary reacts, secondary reacts, but this tertiary doesn't react. But if you take Carros acid, which is H2SO5, both the primary, secondary and even the tertiary also react. As a result of it, you may think that they cannot be distinguished, but they can be distinguished because the way in which they react differs. And the next one is fractional distillation. For the fractional distillation, both these three respond, all the three respond. Now you all know that the fractional distillation is method based on the boiling point difference. You are taught that in your GOC. Now let's quickly see what it is. In the fractional distillation, first you have a mixture, say, of primary, secondary, tertiary amines. First you will heat it. Now depending upon the boiling point, it will vaporize, and here you have condenser. This is called condenser. Now as you keep on increasing the temperature, first one amine goes, and next other amine, and next other amine goes, because the boiling point of these three amines differs. As a result, you will get different products at different time. At one temperature, say primary amine evaporates, it goes through this chamber or this condenser, and then it will finally go to a chamber where it is called a distillate. That is, it is distilled from the solution or the mixture. Here you have condenser. It is used to cool down this. As here you are supplying temperature, you need to cool it, so you are supplying water through this condenser. Now this water cools down this, say, primary amine. It will give you a distillate. Now let us see the next reaction. Now that we are done with the fractional distillation, let us see the Cobalamin test, which we are given in the table. In the Cobalamin test, first treat any primary amine, say RNH2 or PHNH2, with first CHCl3, which is chloroform, in the presence of base, say alcoholic KOH. Now if you heat it, it will give you alkyl isocyanate. Now the structure is pH or R, as you have taken pH or R, NC. Now if you observe, you have positive charge on nitrogen and negative charge on this carbon. Also important thing is that this alkyl isocyanate gives foul smell. And the other products which we are getting here is KCl and water. The mechanism in which it will be proceeded will be taught to you in the questions, so don't worry about it. Now next reaction is Hinsberg reagent. Now Hinsberg reagent is benzene sulfonate chloride, or you can either use paramethyl benzene sulfonate chloride. Now you are told that for this reagent, primary reacts completely, whereas secondary reacts half of the test, but tertiary doesn't react at all. Now let us see the reaction. First take primary amine. If you treat it with this reagent, you are going to get this one, where this nitrogen has attacked on the sulfur, leading to the departure of this chlorine, as you can see it here. Now if you treat it with NaOH, you are going to get this one. This is because this H is acidic, and so it is soluble in alkali, and you are going to get this one. It indicates that this is soluble in this NaOH. And after that, if you treat it with concentrated HCl, and then you are going to get this one. This can also be written as RNH3 plus Cl minus. Finally, if you treat it with any base, say NaOH or KOH, you are going to get back your primary amine. So you have started with the primary amine and tested it with this reagent. You have got one product, and finally you have got back your amine. Now let us see what reaction happens with the secondary amine. With the secondary amine, if you take, you get R2N SO2pH. Now if you add any base, say KOH, no reaction occurs because there is no acidic hydrogen here. Now if you take a tertiary amine, say R3N, if you add this reagent, the reaction won't proceed at all, because you need to have hydrogen or nitrogen to replace this chlorine. As you can see here, in all these primary or secondary amine, they have hydrogen, and whenever they form a compound, they are losing one hydrogen. Here you have two hydrogen, here you have only one hydrogen, as you can see. So they are losing one compound to form a product, but for tertiary you do not have any hydrogen, so they won't react at all. Now let us see the next important reaction. Now the next reaction is reaction with HNO2, as you are given in the table. Now we are not discussing this reaction in this theory because it involves a lot of theory, and we'll be discussing it in the practice problems, not in the solved examples. You also be given practice problems for this. Now the next test is Hoffman's mustard oil test. For this test, the reagent used is carbon disulfide, and next you use HgCl2. Observe that this carbon disulfide is non-aqueous, or it's non-polar. Now in the presence of this carbon disulfide, let us see what primary, secondary, tertiary reacts to it. For primary amine, say RNH2, if you take this carbon disulfide, this lone pair of nitrogen attacks on this carbon, and you are going to get this compound. Now this is simple substitution where you have first negative charge on this sulfur, and this take hydrogen not from the water because there is no water in this solution, from say some other hydrogen or some other compound, like you have RNH2 C S minus double bond S double bond plus on some other compound, let's say. So this hydrogen, this sulfur takes hydrogen from this nitrogen, and you are going to get this one. Now the same is the case with this hydrogen too. Some more molecule takes up this hydrogen, and you are going to get this compound. Now if you treat it with HgCl2, you are going to get a black precipitate, which is HgS. Now In a question, if you are told that you are given an amine and you are treated with CS2 followed by HgCl2, you got a black precipitate, and you are asked to find out which amine it is, you can directly say that it is primary amine, as HgS formation indicates that it is primary. Now for secondary, you have R2NH. If you treat it with CS2, you are going to get this compound. Now if you treat it with HgCl2, no reaction would occur. Now this is an inorganic reaction which you have supposed to remember it. Now for tertiary, if you treat it with carbon disulfide, the reaction won't occur at all. This is because nitrogen here has no hydrogen, and you know that this nitrogen is supposed to have hydrogen for replacement. Now as you can observe here, this reacts completely, and this only responding to half of the test, but this one doesn't respond at all. Now let us see the next important reaction.